evening to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering. And today my content is GTU question paper solution of June 2010. So let's see. Up to question number 4b we already seen. So here question number 4c. Show that P3 and set of 2 cross 2 matrices M2 cross 2 are isomorphic. Here is the solution. We define a transformation T from P3 to set of 2 cross 2 matrices as T of A plus Bx plus Cx square plus Dx cube is equal to A, B, C, D, right, in matrices. Now we are trying to prove that T is 1 1 and 1 2. Okay. So for 1 1, what we have to do? If T is our transformation, to prove 1 1ness, what we have to prove? We have to prove T of x is equal to T of y. We are starting with T of x is equal to T of y and prove that x is equal to y for all x y belongs to the domain. Okay. And for on 2, what we have to do? For any v belongs to the codomain, right, whatever the codomain, for any v belongs to the codomain, here our codomain is set of 2 cross 2 matrices. So for any set of 2 cross 2 matrix, there exists a polynomial which is belongs to P3 such that, call it u belongs to P3 such then T of u is equal to v. Okay. So if we prove this two part, we can prove 1 1 and 1 2. So our mapping T from P3 to set of 2 cross 2 matrices are isomorphic, that we can say. Okay. So now we are trying to prove that T is 1 1 and 1 2. Let Px is equal to A1 plus B1x plus C1x square plus D1x cube, and Qx is equal to A2 plus B2x plus C2x square plus D2x cube, right. So we are taking two polynomials which have degree 3. Okay. Next, T of Px, we are starting with T of Px is equal to T of Qx, and our target is to prove Px is equal to Qx. Okay. Let's see. Starting with T of Px is equal to T of Qx. So T of Px is A1 plus B1x plus C1x square plus D1x cube, that is equal to T of Qx is A2 plus B2x plus C2x square plus D2x cube. Now using our mapping, we know that T of A plus Bx plus Cx square plus Dx cube, that is equal to in matrix A, B, C, D. So here T of A1 plus B1x plus C1x square plus D1x cube can be written as in set of 2 cross 2 matrix A1 B1 C1 D1, that is equal to T of A2 plus B2x plus C2x square plus D2x cube, that can be written as A2 B2 C2 D2. Okay. So now in 2 cross 2 matrices, we know that these two are equal matrix, so we can compare each and every coordinates, right. So we can say that A1 is equal to A2 from this equation. From see, these two matrices are equal, right, and equality of two matrices, that we know that all the coordinates are same, all the entries are same. So we can say that A1 is equal to A2, B1 is equal to B2, C1 is equal to C2, and D1 is equal to D2, right. Now A1 is equal to A2, B1 is equal to B2, C1 is equal to C2, and D1 is equal to D2. So now from this equation we can say that A1 plus B1x plus C1x square plus D1x cube, that is equal to A2 plus B2x plus C2x square plus D2x cube. Okay. And now this is Px and this is Qx. Okay. So Px is equal to Qx. So now we are starting with T of Px is equal to T of Qx, and Px is equal to Qx, so that's why T is 1 1. Okay. Now to prove ontoness, what we have to do? So for any matrix, also for any matrix A B C D belongs to set of 2 cross 2 matrix, there exists Px is equal to A plus Bx plus Cx square plus Dx cube belongs to P3x. Okay, this is P3x such that set of polynomial of third degree such that T of Px is equal to A B C D, right? This is quite obvious. Okay, for any set of for any 2 cross 2 matrix A B C D, there exists a polynomial of third degree polynomial A plus Bx plus Cx square plus Dx cube belongs to the P3x such that T of Px is equal to this matrix A B C D. Okay, so clearly T is onto. Now okay, so we prove oneness and ontoness, so that's why we can say that T is isomorphic, right? So this question is complete now, and this question asked in 3 marks in this question paper. This is question number 4 or question number 4a. Let R3 have the Euclidean inner product. So we have to use Euclidean inner product, that means the dot product, right? Transform the basis S 1 0 0 3 7 minus 2 and 0 4 1 into an orthonormal basis using the Gram-Schmidt process. So this Gram-Schmidt process is actually used for the any normal basis, any basis to convert into a orthogonal basis. Okay, once while if you get orthonormal basis from once while if you get orthogonal basis from orthogonal basis to orthonormal basis, it's quite easy process, because just you have to divide it by each and every vector by its norm. Okay, so first we have to use this Gram-Schmidt process to convert this basis into a orthogonal basis. So first we convert this basis into orthogonal basis, and then from orthogonal to orthonormal we have to just divide it by each and every vector by its norm. Okay, so here our 3 vectors: u1 1 0 0, u2 3 7 minus 2, u3 is 0 4 1. Now let v1 is equal to u1, that is equal to 1 0 0. Okay, first of all find inner product u2 with v1. So u2 is 3 7 minus 2 and v1 is u1, that is 1 0 0. So 3 7 minus 2 dot 1 0 0, simply dot product. So 3 into 1 plus 7 into 0 plus minus 2 into 0, so that will become 3. Okay, now find norm v1 square. Norm v1 square, that is equal to 1 square. Okay, v1 is 1 0 0, so norm v1 square can be written as 1 square plus 0 square plus 0 square, right? So 1 square plus 0 square plus 0 square, that is equal to 1. Okay, these two values, inner product u2 v1 and norm v1 square, that will use in next formula to find v2. Okay, see, here is the formula to find v2. v2 is equal to u2 minus inner product u2 v1 upon norm v1 square into v1. Okay, so what is our u2? U2 is 3 7 minus 2, so put this value here. u2 is 3 7 minus 2 minus this is inner product u2 v1. So this is our inner product u2 v1. You can see inner product u2 v1 is 3 and norm v1 square is 1. So here we put these two values, inner product u2 v1 is 3 and norm v1 square is 1 into v1. v1 is 1 0 0. Clear? So 3 7 minus 2 minus 3 into 1 0 0. So that can be understand by 3 7 minus 2 minus 3 0. Multiply this 3 with this vector. So that will become 3 0 0. So 3 7 minus 2 minus 3 0 0, that is equal to 0 second and third coordinate are same, 7 minus 2. Okay, so V2 is 0, 7 minus 2. Now we want to find V3. For that, first of all we have to find inner product U3V1, inner product U3V2 and norm V2 square. So that's why we find first of all inner product U3V1, that is equal to inner product U3V1, U3 is 0, 4, 1, V1 is 1, 0, 0. So 0, 4, 1 into 1, 0, 0, that is equal to, see, 0, 0 into 1, that is 0, 4 into 0, that is 0, and 1 into 0, so 0. So 0 plus 0 plus 0, that is 0. Now find inner product U3V2. Now what is V2? V2 is we here find just 0, 7 minus 2. And what is U3? U3 is 0, 4, 1. So 0, 4, 1 dot 0, 7 minus 2. So 0 into 0, 0. 4 into 7, that is 28. And 1 into minus 2, that is minus 2. So 28 minus 2, that will become 26. Now find norm V2 square. What is norm V2 square? Here is our V2. V2 is equal to 0, 7 minus 2. So norm V2 square, that is 0 plus 49, 7 square, right? That is 49 plus minus 2 square, that is 4. So 49 plus 4, that is 53. Okay, put all this value in this formula. V3 is equal to U3 minus inner product U3V1 upon norm V1 square into V1 minus inner product U3V2 upon norm V2 square into V2. So U3 is uh, 0, 4, 1 minus inner product U3V1, that is 0, norm V1 square 1 into V1, that is 1, 0, 0 minus inner product U3V2, that is 26 upon norm V2 square, that is 53 into 0, 7 minus 2. So 0, 4, 1 minus this is 0 into 1, 0, 0, so that part will be cancelled out, right, because this part is 0, 0, 0. So 0, 4, 1 minus 26 by 3 into 0, 7 minus 2, so that will become 26 by 53 into 0, that is 0. 26 by 53 into 7, that is 182 by 53, and 26 by into minus 2, that is minus 52 by 53. Okay, so that is equal to 0 minus 0, 0, 4 minus 182 divided by 53, that will become 30 by 53, and 1 minus 52 by 53, so that is actually 1 plus 52 by 53. So when you take LCM, you can understand that 53, and in numerator you will get 53 plus 52, so that is equal to 105. Okay, so this is our V3. V3 is 0, 30 by 53 and 105 by 53. So now this V1, V2, V3 are not orthonormal set of vectors, but that are orthogonal set of vectors. These are orthogonal set of vectors. See, V1 is 1, 0, 0, V2 is 0, 7 minus 2, and V3 is 0, 30 by 53, 105 by 53. Okay, so these three vector are orthogonal set of vectors, V1, V2 and V3. Okay, but now we have to convert orthonormal set of vectors, so that's why we find norm of each vector. we know that norm v1 is 1. See, v1 is 100, so you can understand norm v1 is 1. Now what is norm v2? Here norm v2 square, norm v2 square is 53, so norm v2 is under root 53. And norm v3, that is equal to under root 0 square plus 30 square, 30 by 53 whole square plus 105 by 53 whole square, right? So when you take simplification, that will become norm v3 is equal to under root 11925 divided by 53. So now we have to divide it each vector by its norm. Okay, so v1 is 100. So the required orthonormal basis is given by v1 upon norm v1, v2 upon norm v2, v3 upon norm v3. So that's why v1 is 100, norm v1 is 1, so that's why 100 is same. v2 is 07 minus 2, right? And norm v2 is under root 53, so that's why this v2 upon norm v2 becomes 0, 7 by under root 53 comma minus 2 by under root 53. Then v3 upon norm v3, that can be written as 0, 30. See, what is our v3? v3 is 0, 30 by 53, 105 by 53. Divided this vector by its norm, that is under root 11925 upon 53. So you can see 0 upon this number, that will become 0. Now 30 upon 53, right? 30 upon 53 divided by this number, that will become 30 upon under root 11925. Okay, 53 will be cancelled out, and 105 upon 53 divided by under root